Let's suppose that we have an object that is rolling without slipping. So we have the following wheel that is traveling along the ground. So because the object is translating, that means its center of mass found at point A is moving along a horizontal axis. So that means the center of mass, point A, has linear velocity. So at point A, the entire wheel has a linear velocity given by the following equation. VA is equal to the product of omega, the angular velocity, and the radius of our circle given by the following distance r. Now, the object has two types of kinetic energies. It has translational kinetic energy as well as rotational kinetic energy. So that means if we want to find the total kinetic energy of our object about the center of mass, we have to sum up the two types of kinetic energies, as we'll see in just a moment. Now, let's suppose for the time being that our object, the wheel, is rotating about point B. So it's not rotating about the center of mass, but it's rotating about point B. So that means if we want to calculate the kinetic energy or the total kinetic energy of our object, we have to use the following formula. 1/2 IB omega squared, where omega is the angular velocity of the object and IB is the moment of inertia of the object as it rotates about point B. Now let's recall the parallel axis theorem. The parallel axis theorem states the following equation is true. So IB, the moment of inertia of the object about point B that is not the center of mass, is equal to the sum of the following two terms. So the moment of inertia of the object about the center of mass plus mr squared, where m is the mass of our object and r is the radius of our wheel. Now, let's take this entire equation and plug it into this term here. So we get the following equation. The kinetic energy total is equal to 1/2 IB, which is replaced with the right side. So the following sum of these two terms multiplied by our angular velocity squared. And this is equal to, so now we distribute the 1/2 and our omega squared, and we get the following result. So 1/2 multiplied by our moment of inertia about the center of mass multiplied by the angular velocity squared plus 1/2 mr squared omega squared. Notice omega squared times r squared can be rewritten in the following form. So m multiplied by the square of the product r multiplied by omega. And r multiplied by omega is simply VA, our velocity at the center of mass. So that means we can replace this into this term, so this becomes the following equation. The kinetic energy total of our object is equal to these two sums, where this sum, mVA squared divided by 2, is simply the kinetic energy of the object at the center of mass as it undergoes translational motion, and this term represents the rotational kinetic energy about the center of mass. So initially we said that the total kinetic energy is equal to the sum of the kinetic energies, and that is exactly what we see in the following equation. So, this is the kinetic energy of the object about the center of mass, the point A, where our CM and A are simply the same exact point. So, let's look at one application of this equation in the following example. Let's suppose we have an inclined plane with a height h. Now, the inclined plane is frictionless. We place a solid sphere with mass m and radius r at the top of our inclined plane, and we let it go. So the object, our sphere, travels, rolls without slipping. Now, we want to calculate the final velocity of the object, the sphere, at the bottom of our inclined plane. So we're going to use the conservation of energy as well as this equation. So initially, our object only has gravitational potential energy because initially the object isn't moving. Its velocity is 0. So that means initially, before the object starts moving, it only has gravitational potential energy, mgh, where h is the height, m is the mass, and g is our gravitational constant, 9.8 meters per second squared. Now, after our object ends up at the point h equals 0, it has no gravitational potential energy. All that gravitational potential energy has been transformed into kinetic energy. And in this case, because the ball is rolling without slipping, it's rotating as well as translating. So that means all the gravitational potential energy went into the two types of kinetic energy. So mgh is equal to these two terms: our rotational kinetic energy and the translational kinetic energies. Now notice we are dealing with a solid sphere, and that means the moment of inertia of a solid sphere about the center of mass is given by the following equation. 2 divided by 5 multiplied by the mass of the sphere multiplied by r squared. So we have the following equation, and we simply plug in this entire term into ICM. And now recall the following equation. The velocity at the center of mass is equal to omega multiplied by r. So we want to represent omega in terms of the velocity and the distance r. So we rewrite this equation. Omega is equal to VCM divided by r. So because it's squared, it becomes VCM squared divided by r squared. Notice the r squared appears on the top and the bottom, so that cancels. M appears on each term, so the m's cancel, and we're left with the following result. GH is equal to, so we take out the VCM squared, the velocity at the center of mass squared, and we get VCM squared multiplied by 1/2 plus 1/5. So 1/2 is 0.5, 1/5 is 0.2, so that means this term is 0.7. So we bring it to the left side and we take the radical of both sides, and we see that the velocity of the object at the center of mass is equal to the radical of GH divided by 0.7.